So let me go ahead and formulate the theorem. Let omega 1 and omega 2 be convex sets in Rn, and let x bar be a point in the intersection of omega 1 and omega 2. Now, suppose that the relative interior of omega 1, the intersection of the relative interior of omega 1 and the relative interior of omega 2 is non-empty. Okay, so this is the condition required so that this intersection rule is satisfied. Then the normal cone to the intersection of omega 1 and omega 2 at x bar is equal to the normal cone to the set omega 1 at x bar plus the normal cone to the set omega 2 at x bar. Okay, and recall that the sum of two sets consists of all elements of the form v1 plus v2, where v1 belongs to the first set and v2 belongs to the second set. Now, this condition means that two sets omega 1 and omega 2 intersect each other significantly. Okay, now observe that in this example, here the interior of omega 1 contains all points inside of the set omega 1 here, without this boundary, and the interior of omega 2 contains all points inside of this circle without the boundary. Then obviously the intersection of the relative interior of omega 1 and the relative interior of omega 2 is non-empty. So this assumption is satisfied, and this conclusion holds as well. Okay, so this is a very, very important theorem, and we're going to use this theorem later on in order to develop subdifferential calculus. Okay, so now I'm going to go through the proof of this theorem, and the proof is rather involved. Now I'm going to go through the proof of the normal cone intersection rule by several steps. In the first step, I'm going to show that the sum of the normal cone to the set omega 1 at x bar and the normal cone to the set omega 2 at x bar is a subset of the normal cone to the intersection of omega 1 and omega 2 at x bar. This proof is simple, okay, and it follows directly from the definition. Okay, so the proof goes as follows. We fix any v in this sum then v can be represented as v1 plus v2, where v1 belongs to the normal cone to the set omega 1 at x bar, and v2 belongs to the normal cone to the set omega 2 at x bar. Our goal is to show that V belongs to this normal cone. So we're going to apply the definition of the normal cone to convex sets. So now I'm going to fix any x in the intersection of omega 1 and omega 2. Then we have the following. The inner product between V and x minus x bar is equal to the inner product between V1 plus V2 and x minus x bar, because V is the sum of V1 and V2. So by a property of the inner product, this is equal to the inner product between V1 and x minus x bar plus the inner product between V2 and x minus x bar. Okay, now because V1 is in the normal cone to the set omega 1 at x bar, so this inner product is less than or equal to 0 because x here belongs to omega 1. Similarly, this inner product is also less than or equal to 0. We end up having that the sum is less than or equal to 0. And because this is true for all x in this intersection, by the definition of the normal cone, we have the following. Then V belongs to the normal cone to the intersection of omega 1 and omega 2 at x bar. So we have completed the proof of this inclusion. Now I'm going to continue to complete the proof with the opposite inclusion. This is the second step of the proof. We're gonna show that the normal cone to the intersection of omega 1 and omega 2 is a subset of the normal cone to the set omega 1 at x bar plus the normal cone to the set omega 2 at x bar. In order to prove this important inclusion, we need to recall some important properties of convex sets and functions. Okay, so recall that if f from Rn to the extended real line is a convex function, then the relative interior to the AP graph of f can be represented as all x lambda in Rn times R, such that x is in the relative interior of the domain of the function and lambda is strictly greater than f of x. Okay, so this property can be seen from a figure. So for example, if the function is equal to 0 in this interval from -1 to 1 and infinity outside, then this is the AP graph of f. So how can we represent the relative interior of the AP graph of f in terms of the relative interior of the domain of the function, and then we have the following. Here, the domain of the function is the closed interval -1, 1. So the relative interior of the domain of the function is the open interval -1, 1. And if we apply this result, we see that the relative interior of the AB graph of the function is everything here except the boundary. Okay, so it can be represented as all x lambda in Rn times R, so that x is in the relative interior of the domain of f and lambda is strictly greater than f of x. And the second property we're going to use in this proof is the proper separation property presented in the previous lecture. Two convex sets omega 1 and omega 2 can be properly separated. If and only if the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty sets. Okay, so in order to understand better this property, you can visit the video on convex separation theorem. Okay, so now let me finish the proof of this inclusion by several sub-steps. So now here we're gonna fix any v in the normal cone to the intersection of omega 1 and omega 2 at x bar. Okay, and our goal is to represent v as the sum of v1 plus v2, where v1 belongs to this normal cone and v2 belongs to this normal cone. Now, by the definition, the inner product between v and x minus x bar is always less than or equal to 0 for all x in the intersection of omega 1 and omega 2. Okay, so this is straightforward from the definition. Now the main part of the proof is the following. Now we define two sets. Theta 1 contains all x lambda in Rn times R such that x is in omega 1 and lambda is greater than or equal to 0. Okay, so this is just the Cartesian product of omega 1 and the interval 0 to infinity. And we define the second convex set theta 2 as follows. Theta 2 contains all x lambda in Rn times R such that x belongs to omega 2 and lambda is less than or equal to the inner product of v and x minus x bar. Okay, so again, theta 2 contains all x lambda in Rn times R so that x is in omega 2, while lambda is less than v x minus x bar. Over here, v and x bar have been fixed. Okay, so we will observe the following. Then from the first property recalled earlier, we can have the following. The relative interior of theta 1 contains the following. Contains all x lambda in Rn times R such that x belongs to the relative interior of omega 1 and lambda is strictly greater than 0. Okay, so this is just the Cartesian product of the relative interior of omega 1 and the open interval 0 to infinity. Okay, and the relative interior of theta 2 contains all x lambda in Rn times R such that x belongs to the relative interior of omega 2 and lambda is strictly less than the inner product of v and x minus x bar. Okay, now we're gonna observe the following. The intersection of the relative interior of theta 1 and the relative interior of theta 2 is equal to the empty set. And then we can apply the convex separation for two new convex sets, theta 1 and theta 2. Okay, so how can we observe this? Now we can prove that this is true by contradiction. So by contradiction, suppose that there exists x not belongs to the intersection. So suppose that there exists x in x lambda in this intersection. Okay, then by the property of the relative interior of theta 1 and theta 2, we have the following. Then x belongs to the relative interior of theta 1, of omega 1, and lambda is greater than 0. Okay, and also x belongs to the relative interior of omega 2 and lambda is strictly less than the inner product of v and x minus x bar. Okay, so from here we have the following. Thus 0 will be strictly less than lambda and lambda is strictly less than the inner product of v and x minus x bar. Okay, note that this element x belongs to the relative interior of omega 1, so it is in omega 1, and similarly x is also in omega 2, so x will be in the intersection of omega 1 and omega 2. And here v is in the normal cone to the intersection of omega 1 and omega 2. So by the property written at the beginning of the proof, we have that this is less than or equal to 0, which is a contradiction. So we have proved that the intersection of the relative interior of theta 1 and the relative interior of theta 2 is equal to the empty set. In the next step, we're going to show that we're going to apply the proper separation property to theta 1 and theta 2 in order to derive the main result. Now I'm going to continue the proof of the normal cone intersection rule by applying the proper separation theorem with the set theta 1 and theta 2 defined as above. We have showed that the intersection of the relative interior of theta 1 and the relative interior of theta 2 is the empty set. So by the proper separation theorem, we have the following. By the proper separation theorem, there exists an element W gamma in Rn times R such that the inner product of Wx plus gamma times lambda 1 is always less than or equal to the inner product of W and Y plus gamma times lambda 2 for all x lambda 1 in theta 1 and y lambda 2 in theta 2. Okay, so we have this because we already applied the proper separation theorem on the space Rn times R. Okay, and also there exists an element denoted by x tilde lambda 1 tilde in theta 1 and y tilde lambda 2 tilde in theta 2 such that this inequality is strict in the following sense. The inner product of W and x tilde plus gamma times lambda 1 tilde is strictly less than the inner product of W and y tilde plus gamma times lambda 2 tilde. Okay, so in this step we apply the proper separation theorem to the set theta 1 and theta 2 and obtain these results. Okay, so here we have an element in Rn times R. Now in the next step, I'm going to show that this element gamma is strictly less than 0. Show that gamma is strictly less than 0. Okay, so at first we're gonna have the following. Over here is 0. Observe that gamma is less than 0 because of the following reason. Indeed, the element x bar 1 belongs to theta 1. This is true because x bar is in omega 1 and 1 is greater than or equal to 0. Okay. And x bar 0 also belongs to theta 2. This is also true because when you plug x bar in here, you have 0, okay, and lambda is equal to 0. Here x bar is in omega 2. So by the definition of the set theta 2, we can easily see that x bar 0 belongs to theta 2. Now we can apply the first property in the proper separation theorem to have the following. Then when we plug in, we have the following. We replace x by x bar, okay, and lambda 1 by 1. This is y, and this is lambda 2. So we have the following. The inner product of w and x bar plus gamma times 1 is less than or equal to the inner product of w times x bar plus gamma times 0. Okay, so then we end up having gamma less than or equal to 0. Okay, now our goal is to show that gamma is strictly less than 0, and at this point we see that gamma is less than or equal to 0. So by contradiction, suppose that gamma is equal to 0. Okay, now if we have that gamma is equal to 0, then from these properties of that follow from the proper separation theorem, we have the following. Then we can easily see that wx, because gamma is equal to 0, so we plug in here, we have that wx, the inner product of w and x, is less than or equal to inner product of w and y for all x in omega 1 and y in omega 2. And from the second property, we have the following. Also, there exists x tilde in omega 1 and y tilde in omega 2 such that the inner product of w and x tilde is strictly less than the inner product of w and y tilde. Okay. So because of these properties, by the converse of the proper separation theorem, we have the following. Then by the converse of the proper separation theorem, we have that the relative interior, the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty set, which is a contradiction. Okay, because by the assumption of the theorem, we have that this intersection is non-empty. So this is a contradiction. Therefore, gamma has to be strictly less than 0. Okay. Now I'm going to go through the last step of the proof. Based on these properties from the proper separation theorem, we're going to show that the element V can be represented as V1 plus V2, where V1 is in the normal cone to the set omega 1 and x bar, and V2 is in the normal cone to the set omega 2 at x bar. Okay. So for any x in omega 1, we have that x 0 belongs to the set theta 1. Moreover, the element x bar 0 always belongs to theta 2 as mentioned earlier, then we can apply the first property here to have the following. Then the inner product of W and X, okay, plus 0, gamma times 0 is less than or equal to the inner product of W and X bar plus gamma times 0. This is true for all X in omega 1. Okay, so this inequality can be written as follows. Wx is less than or equal to Wx bar. This is true for all X in omega 1. Okay, so it can also be written as Wx minus x bar is less than or equal to 0 for all X in omega 1. Now, by the definition, of the normal cone to the convex set omega 1, we have the following. W belongs to the normal cone to the set omega 1 and at x bar. Okay, so this is the first result we obtain from these properties. So we have shown that W belongs to the normal cone to the set omega 1 at x bar. Okay, now we're going to apply these properties in the following situation. The element x bar 0 again belongs to theta 1, and the element y lambda, where y belongs to omega 2 and lambda is equal to the inner product of v and y minus x bar, belongs to the set theta 2. Okay, over here actually this is theta 1. Okay. X bar 0 belongs to theta 1, and y lambda, where y is in omega 2 and lambda is equal to the inner product of v and x minus x bar. This element y lambda belongs to the set theta 2. By the first property here, we have the following. Then we have the following. The inner product of W and x bar plus gamma times 0 is less than or equal to the inner product of W and y plus gamma times this element, the inner product of v and y minus y bar. I'm sorry, y minus x bar. Okay, and this is true for all y in omega 2. Okay, so now I'm going to go ahead and simplify this inequality. So this is just 0. Then we have, by moving this to the right hand side, we have the following. 0 is less than or equal to the inner product of W and y minus x bar plus gamma times the inner product of v and y minus x bar. So we can also write it as 0 less than or equal to the inner product of w plus gamma times v with y minus x bar. Okay, now if we divide both sides by gamma with the observation that gamma is strictly less than 0, we have the following. Then if we divide by gamma, we have that 0 is greater than or equal to the inner product of w over gamma plus v and y minus x bar. And note that this is true for all y in omega 2. Okay. Now we can apply the definition of the normal cone to convex sets again to have the following. It follows that w over gamma plus v belongs to the normal cone to the set omega 2 at x bar. Okay. Thus, v belongs to minus w, so w over minus gamma plus the normal cone to the set omega 2 at x bar. And as we know, minus gamma here is greater than 0. Okay, and over there we already showed that w belongs to the normal cone to the set omega 1 at x bar. And note that this normal cone is a cone, so if we take a w and we divide by minus gamma, which is a positive number, the new element is also in this normal cone. Okay, so therefore we see that this element here belongs to the normal cone to the set omega 1 at x bar. Therefore, this is a subset of this sum, the normal cone to the set omega 1 at x bar plus the normal cone to the set omega 2 at x bar. Okay, so we have showed that for any v in the normal cone to the intersection of omega 1 and omega 2 at x bar, v can be represented as the sum of two elements, v1 plus v2, where v1 belongs to this normal cone and v2 belongs to this normal cone. So we have completed the proof of the inclusion. The normal cone to the intersection of omega 1 and omega 2 at x bar is a subset of this sum. And remember that in the first step, by an easy proof, we obtained the opposite inclusion. Therefore, we actually have the equality that the normal cone to this intersection is the sum of the normal cone to omega 1 at x bar plus the normal cone to omega 2 at x bar. And that is the most important result of this section. Now I'm going to present an example to show that the normal cone intersection rule is not satisfied in general. So that means we're going to show that there exist two convex sets, omega 1 and omega 2, such that this normal cone intersection rule the normal cone to the set to the intersection of omega 1 and omega 2 at x bar is not equal to the sum of the normal cone to the set omega 1 at x bar and the normal cone to the set omega 2 at x bar. Okay. So the example is as follows. Let omega 1 be the set of all x lambda in R2 such that x is in R and lambda is greater than or equal to x squared. Okay, so omega 1 is actually the epigraph of the function y equals x squared. And then the set omega 2 is given by all x lambda in R2 such that x is in R and lambda is less than or equal to minus x squared. Okay, so omega 2 is the this set all x lambda in R2 so that x is in R and lambda is less than or equal to minus x squared. Then, as we can see from this figure, the normal cone to the set, and here x bar is the origin, so x bar is 0, 0. Okay, then we can see that the normal cone to omega 1 at x bar is all vectors in this direction. So it is the following set: the Cartesian product of 0 and the interval minus infinity to 0. Okay, and similarly, the normal cone to the set omega 2 at x bar is the Cartesian product of 0 and 0 to infinity. Okay. Also, we see that, moreover, the intersection of omega 1 and omega 2 here is a singleton, that is x bar. Okay. So we easily see that the normal cone to the intersection of omega 1 and omega 2 at x bar is the whole space R2. Okay? And observe that the sum of the normal cone to the set omega 1 at x bar and the normal cone to the set omega 2 at x bar here, if we compute this sum, then we have the following: is equal to the Cartesian product of the set, singleton set 0 and R. Therefore, here this inequality is not satisfied. Okay, so the reason here is that the condition given in our main theorem is not satisfied, because the relative interior of omega 1 can be given as follows: is all x lambda in R2 such that x is in R and lambda is strictly greater than x squared, and also the relative interior of omega 2 is the set of all x lambda in R2 such that x is in R and lambda is strictly less than minus x squared. Therefore, in this situation, we see that this intersection is equal to the empty set. Okay, so without assuming that omega 1 and omega 2 intersect each other significantly, in the sense that this intersection has to be non-empty, then the conclusion of the theorem is not guaranteed.